So today's video is going to go over factoring polynomials with our first method called the greatest common factor. Just as a review, we've already talked about the zero product property. And the zero product property was an important tool that allowed us to solve equations, but we had two things that needed to be true. We needed to have it as a product of two things, and that product must have been equal to 0. So for example, we could solve something like x plus 1 times x minus 6 using the zero product property, because there is a multiplication between both of them, so it is a product of two or more things, and it's equal to 0. What we're going to investigate today is what happens if we have a polynomial equation, maybe something like 4x squared plus 8, that's not written as multiplication. So how could we rearrange or rewrite this equation to use what we already know? So as we talked about before, the zero product property must have a product as its original equation. So one vocabulary word for today is the word factor. And what we can see here is that the word factor is going to be written or used as a verb and as a noun. So there is a difference between how we use the language. So the most important thing that we're studying today is factoring as a verb. So factoring is an action. It means you need to rewrite something as a product of two things. So for example, if we come down to the bottom here, let's say we're supposed to factor the number 12. So right now 12 is written as a number. This is not a product. So what I could do is I could write an expression that's the same number as 12, but rewriting it as a product. So for example, 3 times 4. So over here, this is written as a product. So the action of rewriting it, starting at 12 and rewriting it as 3 times 4, that was an action called factoring. Now, when we actually do the action of factoring, we get something called factors. And factors as a noun represent the individual pieces that make up a multiplication problem. So if we look here, there's two factors here. We use the factors 3 and 4 because both of those factors are being multiplied together. So let's look at the number 12. I could factor it in many ways. Maybe I'm going to do 3 times 2 times 2. This is one way of factoring it because I wrote it as a product. And in this case, I have 3 factors. And those factors are 3, 2, and 2 because those are the numbers that are participating in the multiplication problem. The last vocabulary word for today is factored form. Factored form is what it looks like as when we rewrote it as a product. So 12, if we wrote it in factored form, could be something like 3 times 4. Another factored form could be 3 times 2 times 2. So there, in this case, for the number 12, there's more than one factored form. So the idea for today is we originally looked at a problem, let's say something like 4x squared plus 8 equal to 0. What we said was the problem there, that it was not a product. So we can't use the zero product property. So what we can do is we can factor to make it a product. We'll see how to do this in a moment, but I could rewrite this as 4 times x squared plus 2. And now this is written as a multiplication problem. Now, the one big thing to kind of preface our work today is that when we factor polynomials, there are a ton of different techniques, and we're going to study a ton of them as well, but today we're just going over one of those techniques, and we're just using the greatest common factor today. So to find the greatest common factor of any expressions, we want to break it down into more manageable pieces. So let's say, for example, I had to find the GCF of something like 4x squared plus 8x. What our directions tell us to do is let's look at each term. And first of all, let's look at the coefficients of just those terms. Let's find the GCF of just the coefficients. So if I just look at the coefficients, 4 and 8, the biggest number that goes into either 4 and 8 is the number 4. Then what it says to do as the second step is to find the greatest number of each variable that can be factored out of each term. So in other words, look at the variables second. So this term here has x squared, which means there's x being multiplied twice. This term has x being multiplied once. So what's the greatest number of x's that I could take away from both of those? Well, just one x. So the GCF of these two would be 4 times x. Another example, let's say I had something like 2x to the third, y to the fourth, minus 6x squared, y to the fifth, plus 16x to the third, y to the first, z to the third. This seems like a harder problem, but let's write the GCF. And again, what we can do is we can find the GCF by parts. First, let's just look at the coefficients. So the number 2, the number 6, and I'm going to disregard the negative for a second, and then the number 16. The biggest number that goes into all three of those is the number 2. Now what we see here is there's x's, there's y's, and there's z's. So let's do it part by part. This term has x to the third power. This term has x to the second. And this term also has x to the third. So what's the greatest number of x's that I could take from every term? Well, this is the smallest, so I can take 2 from this one. I want to be able to take 3 from all of them, so the biggest number of x's I could factor out from both of them would just be 2. Now let's look at the y's. So this expression has y to the fourth power. This expression has y to the fifth power. This expression just has y to the first power. So what's the greatest number of y's that I could take from every single term? Well, this has 1, this has 5, and this has 4. So if they all have to give the same amount, we're going to be limited by the smallest one. So we'd be able to take 1 y from every expression. Now what's interesting is to look at z's. This term back here has a z in it, but none of the other terms have a z in it. So if only one term has a z in it, it's obviously not going to be a common factor for all the other terms because they don't have a z in it. So this is our greatest common factor. So the real reason that we want to use factoring, like specifically the GCF, is so that we were able to then employ or use the zero product property. So like, for example, if we had something like we looked at before, let's say something like 4x squared plus 8x was equal to 0. We cannot use the zero product property because it's not written as a product. It's written as a sum. So what we could do is we could find the GCF and rewrite it. So let's look at the GCF of 4 and 8. So the GCF of the first number is 4. Then we look at the variables. This term has x squared in it, and this term has x to the first. So each of those could afford to give away 1x. So now, what would that be multiplied by? In other words, if I factored that out, so if I took out a 4x from both of these terms, what would I be left with? Well, 4 and 4 would go away. There used to be 2 x's on top, but I took 1 away, so there'd be 1x left. Then there's a plus sign. So over here, 8 divided by 4 gives me 2, and x divided by x goes away. So now I've successfully rewritten the original problem here as a product of this thing, 4x, and this other thing, x plus 2. So now, as it says here, we can use the zero product property to solve. One of these things has to be equal to 0. So either 4x was equal to 0 or x plus 2 was equal to 0. So the answers could have been x was 0 or x could have been negative 2. So our final examples today are when we put everything together. So what we're supposed to do is we're supposed to solve equations like this. What we need to do to solve equations right now with polynomials is we need to use factoring to make sure that it's written in factored form, and then we're supposed to use the zero product property. So a quick little how-to on how to do that. The first thing for every problem, always make sure it's equal to 0. Then we should use factoring to get it in factored form and then use the zero product property. So for example, this one's already equal to 0. So step number 1 is checked off, but it's not a product. So what I need to do is find the GCF and rewrite it as a product. So the GCFs of the numbers 8 and 24, the biggest number that goes into both of those is 8. If I look at the variables, this term has 2 y's being multiplied, and this term has 1 y being multiplied, so they could each afford to give away just 1 from both of them. So that's my GCF. Now to figure out what's left over in parentheses, I'm just going to divide both terms by that GCF. Just imagine that I unfactored it. So 8 divided by 8 is 1, y squared divided by y is just 1y. And there's a minus sign. 24 divided by 8 is 3, and y divided by y cancels out. So we've successfully rewritten it as a product of this term times that term. So either 8y was equal to 0 or y minus 3 was equal to 0. So here y would have been 0 or y could have been positive 3. Moving over to the second example, we do see that it's already equal to 0, but it is not written as a product. It's a sum. So what we need to do is we need to factor out the GCF. So if I look at the numbers 4 and the numbers 12, their biggest common factor is 4. Then if I look at their variables, this has 2 x's to give away, and this has 1 x to give away. So the maximum number of x's I could take from all the terms would just be one of them. So I'm going to imagine what would be left over then. So if I took 4x away from both of them, well, 4 divided by 4 is nothing, or just 1, excuse me. X squared divided by x is x. Taking out the GCF here, 12 divided by 4 is 3. X divided by x goes away. And it's important we can know that we can always check our work to make sure we found the correct factor if we just multiply it back. So like if we check our factoring, if I distributed that 4 times x, and then it would be plus 4x times 3, which would be 4x squared plus 12x. So I know that I factored it correctly. So I just did that to check. But now once we have it in factored form, in other words, it's a product, we can now solve using the zero product property. So either this thing was equal to 0, or this thing was equal to 0. So the two possibilities for x, like if we divide by 4, we would get 0, or the other side, we would get x equals negative 3. Now example number 3 is here to show us that it's not equal to 0, so we just need to get it equal to 0. I like to keep my leading coefficient positive, so that's why I'm going to choose to add 10a squared to both sides. Negative 10a squared and positive 10a squared adds up to be 0, and then here I have 10a squared plus 8a. And I did take the liberty to write that in standard form. Now our next step is it's not a product, right? So we need to look at the GCFs of the numbers. So 10 and 8. The biggest number that's divisible into both of those is the number 2. And then I look at the variable terms. This has a squared, and then the other one is just a to the first power. So the maximum number of a's I could divide from all the terms would just be one of them. So in other words, what would be left over if I undistributed or if I divided by 2a? This would leave me 5a. And over here, if I divided by 2a, a divided by 2 is 4. And the a's cancel. So now we do have it as a product of two things that is equal to 0. So either 2a was equal to 0 or 5a plus 4 was equal to 0. So our possible answers were a equals 0, or if I subtract 4, I would get a is equal to negative 4.